Hi, welcome back to Moose and Chemistry. This lesson is going to be on Nuclear Chemistry Thorium Decay Series 2. In the last pathway, we saw Thorium-232 decay into Lead-208. This path is very similar, except for when we get to the end. Now remember that the A particles are alpha particle, and it talks about alpha decay emissions. And alpha decay emissions, whereas a 4He nucleus, or 4,2-alpha, which is called an alpha particle, is removed from the parent atom to change the element into a different element using this equation. A represents the atomic mass number, that's the AMU, and that's the number of protons and neutrons. And Z represents the atomic number, which is the number of protons. So AZX is going to yield A minus 4, Z minus 2, Y, which is our new element, and then of course our alpha particle. Okay? This funny looking B is our beta particle, and it's beta decay emission, so it's 0, negative 1e or 0, negative 1b, and neutron is converted into a proton, changing the element into another element and releasing a beta particle. Again, remember that our A represents our atomic mass unit, the number of protons and neutrons in the nucleus of an atom, and the Z represents the atomic number, which is the number of protons in the nucleus of an atom. In this case, AZX is going to yield A over Z plus 1. So we're adding a proton, but we're not adding a proton bringing one in. We're changing one of the neutrons that are already in that particular element into a proton. And it's going to make our new element and, of course, releasing our beta particle, which is this right here. All right, let's go ahead and do this. So Thorium-232 undergoes alpha decay. It becomes Radium-228. Radium-228 undergoes beta decay. It becomes Actinium-228. Notice that even though they have the same atomic mass number, our number of protons have changed from 88 to 89. We've made a brand new element when we did that, okay? All right, changing neutrons just changes the mass. Changing protons changes the element. All right, so then Actinium-228 undergoes beta decay again, and we change another neutron into a proton, and we get Thorium-228. Thorium-228 undergoes alpha decay and loses 2 protons in the atomic number, and also 2 neutrons. So now it's 224/88 radium. And notice that this radium is 224 here, and this radium is 228 here. The only difference is the number of neutrons, not the number of protons. Pretty snarly, huh? All right, let's move on down the list a little bit further. Again, we could be doing these equations that we have in the upper right-hand corner right here, this one and this one, but for the sake of the length of the video, we're just going to go ahead and do this in our head. All right, so Radium-224 undergoes alpha decay, it becomes Radon-220. Radon-220 undergoes alpha decay, it becomes Polonium-216. Polonium-216 undergoes alpha decay again, it becomes Lead-212, Pb-212. Now, Lead-212, you think that lead is the stable isotope, but no. Lead-12 is not stable, it's slightly radioactive, right? So it's undergoing beta decay, and that means it's going to pick up turn a neutron into a proton, it's become the element bismuth. Now bismuth then undergoes alpha decay again and becomes thallium. Now thallium, on the other hand, undergoes beta decay and turns a neutron back into a proton. And then we get our base lead, which is Lead-208, which is a stable element of lead, or stable isotope of lead. Now, let's look at our half-life table real quickly. Thorium-232 has 1.14 times 10 to the 10th years, so that's a very long time. Radium-228 has 5.7 years for its half-life. Actinium-228 has a half-life of 6.1 minutes. Thorium-228 has a half-life of 1.9 years. Okay. Radium-224 has a half-life of 3.6 days. Notice that's quite a bit of difference from Radium-228's half-life, which is 5.7 years. Okay, so then the half-life of Radon-220 is 55 seconds. The half-life of Polonium-216 is 0.14 seconds, so that's a very short half-life. The half-life of Lead-212 is 10.6 hours. The half-life of Bismuth-212 is 61 minutes. The half-life of Thallium-208 is 3.1 minutes. And then, of course, Lead-208 is stable, or what I like to call the end game. That's where it's not going to decay any further. Will you guys be snarly? I will see you back here at Emission Chemistry!